I'm Alex from Datalex, and today I'm excited to show you a powerful Python Streamlit application. With this tool, you can input your data, build a regression model using LightGBM, and then leverage SHAP to explain your model's predictions. So we'll start with the dataset of hospital patients' data, and we'll try to predict the medical charges they will have to incur. So we'll start with the dataset where we already know the charges. The model learns from that and then is able to predict charges based on their information. And we will be able to tell how accurate the model is, as well as be able to explain what contributes to that medical cost. Okay, so we'll start by importing the data and identifying our target variable. So in this case, it's the charges, called charges. In the import tab, there's many transformations we could do that are useful. Sometimes the data is too big and we have to sample down, or we have to do log transformation, very, very common. But we'll keep it simple for now and skip these steps. In the Explorer tab, we are able to visualize correlations with our data. So for example, we could plot age against charges. And we could observe, for example, that as the age increases, see that this is going up. It means that there's a tendency as the age increases to see the charge also go up. I often use this feature after building the model to confirm that the insights I've gathered are, true and they kind of match what we see directly in the data. Next, we have the Model tab, and this is really where the magic happens. This tab builds our model and provides us with its accuracy metrics. So in this case, see here that the R-squared test is 82%. So it says that 82% of the variation in the charge is explained by the variables in our input data. So that's pretty good. Could be better, but it's still pretty good. We can learn something from that. Is in a way reliable enough for us to learn from it. And the next step would be to look at the model's explanation. So this kind of looks inside the model and says what things it contributed the most for the charge. So in this case, and they are ordered by importance. So the smoker is the one who contributes the most to the charge. Then age. In age, remember that we saw in Explorer, we already got an intuition that as age goes up, the cost goes up. So it's confirmed here. And then BMI, and etc. We can also drill down into individual patients in this case. Each record here is a patient. So for example, we could say that patient number 3, the actual cost was 9,300 and the predicted cost was 9,459. So it is fairly close. Okay, and then it says what factors contributed to this cost. So the bigger the bars, the more the contribution. So it says that smoker, yes, equals 0, means it's not a smoker. And the BMI is also fairly reasonable. So these two factors are the biggest things in actually keeping the cost at 9,000, a little bit lower. Age 46 is the thing that typically would make the cost go up, because as the age go up, the cost goes up, and etc. So this is a way you can inspect what the model is doing and understand and get the insight of what things are actually contributing to that medical cost. So we'll look at another example. So here the value was, the actual value was 33 of the cost, the medical charge. And the one that the model predicted was 34.792. So still fairly accurate. And it says, for this particular patient, that smoking was the biggest contribution by far. And then we also have the BMI, which is 31, is a little bit higher than we had on the other patient. And so that contributes to an increase of the cost. The age being 19, which is a low age in a way, or a younger age, it means that makes the cost a little bit cheaper. But in general, smoking and the BMI are the things that contribute to the biggest cost. And it was still fairly accurate with the prediction. Of course, this data works not only for medical, but you can input here any kind of data. And so, yeah, it's generic. And really, one of the main reasons I use this tool for is not necessarily to deploy a model, to build a model and then deploy it, but it's instead to uncover insights from the data. So for example, this one kind of let us understand what contributes the most, what correlates the most to the cost of the medical charges. And you know, I would almost summarize it as answering two questions. Is there a strong correlation between this patient data and the charges? And in this case, yes, that is the evaluation metric. Because if this is a no, we cannot really use these explanations. But if it's a yes, then we have enough confidence to use these explanations. And then the second part that I use this for is to understand what is really explaining those medical charges. Okay, regarding the technical details of this application, it uses LightGBM, which is a gradient boosting tree algorithm developed by Microsoft. Previously, I created a similar functionality using neural networks in PyTorch that I covered in one of my previous videos. And while the neural networks generally offer good accuracy, they are slower compared to LightGBM. It's very interesting to see the neural network train in real time and see the model learn from the data. But in this case, in some cases, speed is a important factor. So LightGBM is specifically designed for speed and scalability. So it also is able to take a lot more data, making this ideal for large data sets. So this is why I kind of went, I choose to return in a way to a classical machine learning model for my main regression tasks. Yeah, neural networks are of course incredible and can cover and can model a wide range of problems, but they aren't always the most efficient tool for every test. That's kind of my technical insight here. Additionally, all of this is put together using a web framework called Streamlit, and now it allows me to have like a standalone app that allows me to quickly run a regression analysis without having to open my code editor and kind of do all those things by hand. It kind of just goes faster once you have a pre-programmed application for that. Thank you. I hope that is useful. Bye-bye.